recording anything right now, just the audio. Something about less than 1. Because I want you to think about it. Let's say I take the number 16. What's half of 16? 8. What's half of 8? 4. What's half of 4? So what's happening to that number? Is it growing or is it decaying? It's decaying, right? So when the constant factor is what? When that constant factor so you can use b, by the way, for a times b to the x, or an f, either one. When the b is less than 1, but remember, it had to be greater than something as well. Had to be greater than 0. Remember, when it was 0, that means we're repeatedly multiplying by 0. That's not an exponential function. Okay, so when the base or the constant factors between 0 and 1, we have a decay. Okay, so the second one, right? Growing or decaying? Why is it going to grow? It's bigger than 1. I want to point this out. I want you to think about this. There's a big reason why with exponentials I harp on this so often. If I take times 5/3, yes, I'm multiplying by 5/3, but let's rethink that. I'm multiplying by just 5 and dividing by what? 3. So if I multiply by 5 and divide by 3, I'm multiplying by a little bit bigger. So what's going to happen to that number? It's going to grow. And so Elizabeth said earlier, if the base is greater than 1, we see growth. Now, no one else did this earlier, I don't think, because I suggest you not. But I want y'all to think about that last one. Elizabeth, when you typed it in the calculator, what did you see? Why not? Anyone know? Why she didn't see anything? Any guesses? No, it's not that. What's 4 times negative 2? Or well, let's just use the 3. What's 3 times negative 2? Negative 6. What's negative 6 times negative 2? Positive 12. Positive 12 times negative 2. So is that growing or decaying? Now, the absolute value is growing, but it's going from positives to negatives, back to positives, back to negatives. So is it growing or decaying? Neither. Remember, we looked at this last week. Can someone go grab the camera? I just want to show you all this on the calculator again, because we missed this, or we're forgetting this detail. Right here. So remember, here is that base of 0. Notice, is there really anything on this graph when the base is 0? See, that's b to the x, that's the function. Thanks, Chrislyn. When b is less than 1 but greater than 0, that function's exponentially decaying, right? Decay. And then all of a sudden it starts to grow once the base is greater than 1. But look again when it is negative. Does that look like a function to you? No. The base cannot be 1, the base cannot be 0, and the base cannot be a negative to be an exponential function. These are the requirements for growth and decay. Base is between 0 and 1, decay. Base is greater than 1, growth. Anything else, you know what it's not? It's not an exponential function. Okay? So let me say that one more time. If the base is between 0 and 1, we're making that number smaller so it is decaying. If it's greater than 1, we're growing. If it's anything else, what is it not? It's not a function. Yeah, I don't think it's a function at all, but it's definitely not an exponential function, right? So make sure you please go get those for error models out that I gave you all last Friday. Because that's an important part of this next little piece. Yes, ma'am. That's a fantastic question. If I can find it in my hodgepodge of garbage over here.
Give me a clean ever.
Aha! Yes, you can.
I'm gonna make that.
I think I might need it.
Well, remember, I can just use your test as well. Anybody not have the logarithms and functions intro for our model?
So what we write this on the broken?
Say it again.
We write this on the broken.
Say it louder.
We write this on the broken.
Yeah, it's growth and decay, ain't it? No, I just use your test to assess those skills. Hey guys, please hurry and get this down so we can continue with the lesson. I want to get at least into what a logarithmic function is. Yeah, or at least end an exponential. I just realized I never had my coffee this morning. I feel so much better. Just taking a few sips. Yes, ma'am. So, remember, if the base, which is your constant factor, is greater than 1, that number is going to constantly what? Grow. If that base or constant factor is greater than 1, the function is going to constantly grow. If that base is between 0 and 1, then it is going to decay. Now, I do want to point this out. Please notice, do I have a less than or equal to on either of these?
No.
No. Because if I'm multiplying by 0, what does it stay? 0. If I multiply by 1, what does it stay? Yeah, whatever it was. Yeah. So it's not constantly growing or decaying. So there we go.
And then you would just say negative numbers.
If it's a negative number, it gets funky. Remember how it was like, yeah,
So neither.
yeah, neither. It's not an exponential function. And I will say that if the base is 0, the base is 1, the base is negative, it's not an exponential function. So the way you could say that, I guess,
Negative numbers.
if the base, my constant factor, is less than or equal to 0, or if the base equals 1, not an exponential function. Notice that's the plain way to write that. Or mathematical way to write that, I should say, not plain. Right, using inequalities, equations, things like that. Mary, I'm gonna have to look for the proficiency for this. So remember we did a recap on lesson 1. We didn't do lesson 1, but lesson 1 was just linear versus exponential. What makes a linear a linear?
Rate change.
What type of rate of change? Constant additive called a slope, right? That linear graph, that constant additive rate of change, y equals mx plus b. And if it was exponential, then it was a constant multiplicative rate of change called a constant factor, right? Exponential curve, all that fun stuff, a times b to the x. So now we're on the exponential growth and decay, things like that. So I wasn't sure if I was going to cover this, but I decided to put it on the proficiency scale, and I am going to cover it probably tomorrow or Wednesday. We're going to talk about power rules. Does anyone remember what I mean by a power rule?
No.
Nothing?
The power.
Thank you, the power, but like, what's x to the third raised to the fourth?
Aren't they added together?
Not the seventh here,
Oh, the 12.
it's to the 12th.
Oh, because of parentheses.
Because look, for instance, so we're raising a power to a power, we end up multiplying the powers. Now the real reason behind that is, what does it mean to raise something to the fourth? It means to repeatedly multiply how many times?
4 times.
4 times. Okay, so really what I have is 4 groups of 3. And what y'all were talking about, or what some people were thinking about with adding, this is when we add. Because essentially, what am I saying? How many x's do I have right here?
4.
No, right here. I have 3 x's being multiplied, right? X cubed is multiplying 3 x's. And then what am I doing here? I'm multiplying by 3 more x's, so it's increasing. So what do you do when things increase? Bless you. You add. And then we multiply by 3 more x's, so we add again. And then we multiply by 3 more x's, so we add again, right? So remember, what you would have probably seen is something like, I don't know how a previous teacher might have written it, but something to this effect. When you're multiplying, you end up just adding the exponents. When you raise a power to a power, you end up multiplying the exponents. And what about if I take x to the 7th divided by x cubed? They subtract, right? So we get x to the 4th. And it really goes back to the core of just thinking through what an exponent is, right? When I take 4x plus 3x, I'm taking 4x's and adding 3 more x's. So I'm adding 7x's. Multiplication is repeated addition. In the same way right here, I am multiplying by 3x's, I am multiplying by 3 more, multiplying by 3 more, multiplying by 3 more. So I keep adding how many x's I'm multiplying, right? So that creates x to the 12th. That also explains why 4 groups of 3, I just multiply the powers. And then if you break this down, and we'll do more with this, there's just a quick recap of what you did in Algebra 1. 1, 2, 3, 4, 5, 6. There's 7 x's dividing by 3. And what is x divided by x? Not 0. 1. Right? What is x divided by x? And x divided by x. And how many x's am I left with?
4.
See, I just subtracted, or I took away some of those x's that I'm multiplying by. So if we go back to that core idea, power rules, not too bad. We're going to use those with logarithmic properties later. But foundation, creating table and graph for an exponential function, identifying features, and notice I've identified exactly which features, not intervals of increase and decrease for this one. Explaining what a logarithm is, which we have done, and then using power properties to simplify expressions. So that's a little bit, that's really what we're doing with this current set of lessons. We're going to go into logarithms later, right? So we did do growth or decay, but most of the rest of this is a later lesson. Okay, did that calculator exploration instead of doing the textbook, because the way the textbook did it was silly. Here we go. So this is what I want us to do quickly with the time that we have left. What we're going to do is just in general look at a basic exponential growth. So here's an example. No, I did not. So I'm going to say sounds like we're scrambling for our papers, so we're just getting them back out. Yeah. Anyone know how I quickly got those points? Yeah? You said exponents?
Which points?
Oh, these points right here that I just put on the board. Don't forget, any function can be inputs in, inputs out, or outputs out. What's 2 raised to the 0?
1.
1. What's 2 raised to the first?
2.
2 raised to the second? 2 raised to the third? And then remember, a negative exponent is not repeated multiplication, it's repeated division. So I have 1 divided by 1, 2. The negative 2 is 1 divided by 2 2's. But what is 2 times 2? 4, right? Okay. That's all I did to get these points. 0, 1, 1, 2, 2, 4, 3, 8. That's it. And then backwards, negative 1, 1/2. Okay? So, inputs in to get outputs out. When we get to more complicated functions, other than just 2 to the x, we might want to do a little bit more with it, but we need to know those kinds of things. Another thing to point out is my understood y-intercept is 1, right? So I'm starting at 1 and repeatedly multiplying by 2. That's another way to see that, okay? So, what would be the domain of this function? Negative infinity to positive infinity. Anybody want to push back on that or ask a question about that? No pushback? No questions? Okay. Can someone explain why then, if we're all in agreement? Okay, so inputs, what else?
It never stops moving across the X or Y axis.
So it never quits going across, was it the X or the Y? The X, so notice it never quits going to the left, so that my minimum X is negative infinity. Does it ever quit going to the right? So my maximum is positive infinity. Cool. That's all I want to see. Range. You think so?
What do you say?
He said same thing, negative infinity to positive infinity. Not potentially. Look at it again. Bless you. Remember, this is one of the last things I left off on Friday. Remember how I pointed out that it is approaching that line that I just drew? And remember the name of that line that I just drew? This black one I just drew right here, that it's approaching but not quite ever getting to. It's what? It's an asymptote. It's actually right here. Asymptote. The line that or curve that a function approaches at some infinity. So line or curve, I don't even need to say function, a relation approaches at some infinity. Because I do want you to notice, if I keep going with this, what kind of numbers am I never going to get for my outputs? Well, I got whole numbers here. Never going to get into the negatives, am I? I constantly have a positive divided by a positive, so what am I never going to get to? There's also another number that I'm never going to get to. Well, yes, I'm at, you can get really funky stuff. But yeah, I'm definitely never going to get a 0, am I? If it's a positive divided by a positive, I never get to 0. So what is my range? What is my minimum y value? What does it get close to? It gets close to 0, but does it ever get there? So how am I going to write that it gets close to 0, but never quite gets there? With a parenthesis, right? Remember that bracket means we get there, that it equals it, but do we ever get to that 0? Nah. But what's the maximum y value? Positive infinity. So never quite gets here. Now that can change with transformation. But yeah, it never quite gets here. And then it never stops going up, maximum y. So what's my asymptote then?
0.
Okay, close. There's something with that 0, but what does that 0 equal? Now, x equals 0, so I want you to think about this point right here. This is the point 1, 0. This is the point 3, 0. This is the point negative 2, 0. So what are you saying?
Y.
You see how that y value is 0 every time? Doesn't matter what x is. On the x-axis, the y value is? That's why for x-intercepts, the output was always 0. So y is equal to 0. Notice with those kinds of horizontal and vertical lines, just draw a few points and you can clearly see, is it what x equals or is it what y equals? When I found that out and realized I didn't have to memorize vertical versus horizontal lines, it blew my mind. I was like, frick, that's so much easier. I just had to memorize, like, oh, y equals 7. And I always got screwed up because I was like, oh, y is a vertical number, so why is it a horizontal line? Because the y value is always 7. Or in this case, y is always equal to 0. All right, intercepts. Do we have an x-intercept? Nope, never gets to the x-axis. Notice it's approaching, but it never gets there. Do I have a y-intercept? It's 1? I need something a little bit more than just 1. Thank you. It's an intercept. It's a point, right? It's got to have an input and an output. If I substitute 0 in, I get 1 out. And so remember, we're not doing intervals of increase, decrease. That's just silly with exponentials. Okay. In behavior, though, On the left-hand side, what's x approaching? Not 0. I would say, does it ever quit going left? So what's on the left-hand side? Negative infinity. We gotta be careful about that. And notice what is y approaching on that left-hand side?
0.
That's the whole idea of the asymptote. That's why I defined it this way earlier. Remember, it's a line or a curve, a relation approaches at some what? Infinity. As we go to this infinity, y goes towards 0. It doesn't get there, but it goes towards it. On the right-hand side, it never quits going right, never quits going up. So we get this. Okay? Really quickly, over here we got an exponential decay. That base is between 0 and 1. And what's that domain still going to be? Negative infinity to positive infinity. What's the range going to be? Same thing, isn't it? Still going to approach the x-axis? Again, we can have transformations, but there's that. What's my asymptote? Still y equals 0. And the intercepts, still 0, 1. The only thing different is my end behavior, really. Now as x goes to negative infinity, what does y go towards? So as we go left, it's also going up to infinity. And on the right-hand side, as x goes towards infinity, y goes towards going towards 0. Remember, again, that's the idea of an asymptote, right? It's what that function approaches at some infinity. We're going to pick up with logarithms tomorrow, so we'll be hitting logarithms pretty heavily Tuesday, Wednesday, Thursday, testing either Thursday or Friday or Monday. But we'll do a good bit of review for those of us who are going to need to take the midterm. Next week we will also just review in general so that some of you can show me proficiency with concepts, even if you don't have to take the midterm, to try to get that proficiency scale score up. So I'm going to go, I got through Unit 5 last night, but I did not get those or go back to old units. I will get that done soon. Did I give you all your Unit 5 test back?
I don't think so.
I don't think so either.
Skinny queen.
I will make sure I find it before tomorrow.
I would rather fail. I would rather fail. I'm joking. I'm not sure if I fail.